Okay, hello everyone and welcome to today's class. This is the first episode in my new Assembly School series, and we're gonna start right away by setting up our environment. I'm, as usual, going to code from a Linux VPS that I have. So I'm just gonna set up my stuff real quick. Introduce it. Done. Okay, so the first thing we're gonna do in a Linux Debian machine is log in as root, and then we will install some packages. We're gonna need three things basically. We're gonna need a assembler, and for that we're gonna use something called NAS. So N assembly. And we're gonna need a linker, LD, and we're gonna need a debugger, GDB. So to install that on a Linux machine, we do apt-get update to update our list of packages. And then we just do one command to install everything, and I'm not going to wait for this because my connection is a little bit slow because of a bad router. I haven't had time to replace that yet. Apt-get install, and we need NASM, and we need, for LD, the package is called binutils, and it's usually installed on every system, but just in case. And we're gonna need GDB. When we have installed this, we can begin creating our first assembly program. And the extension which is commonly used is either .s or ASM, and I like ASM. It doesn't really care what extension. And I'm going to use VI as a text editor to code this stuff. You can use Nano, or you can use any text editor you want. And we're going to be coding 32-bit Intel assembly. So let's start by first specifying that we need 32 bits. And then we will need a little bit of boilerplate that we have in every program. So basically the assembly file, the code file, is built up like a map of the memory. So we have different memory segments, or sections like they are called. So we have one section called text, and this is where we put all our code. And this is usually a read-only segment during runtime, and it is executable, which means that it can execute instructions. And all these commands, all these instructions, these are instructions directly to the CPU. So, yeah. And maybe it should be big SM a little bit. I think so. Let's try it out. And then we have the data segment. So the data segment, that is where we store our variables, basically. Our data that we're gonna mutate and use, text strings and all different types of variables. And every line in a assembly program has a memory address. So in hex it looks basically like this, for example. And then we have some data in this case. And then we have another, and then some data. So this is how it's built, but we don't specify the memory addresses. Those are calculated automatically, but it can be good to know that. So this is a global address that is pointing towards a specific place in memory. Instead, we are using something called labels. So a label is like not like a variable, but it's, let me show you. So let's say we want to store a string on the data segment, and we can call this str, for example. So a label is done by typing a name and then a colon. And then we can give an instruction. So db means that whatever we put here will be put onto memory as is. It's not going to be formatted or changed in any way. So we can, for example, put the string hello. And then we want a new line character, for example. And that is, I usually do it like this, the hexadecimal character A, which means 10, and that's the ASCII character for a new line. And let's terminate the string properly with 0 byte as well. So in assembly we need to specify all these things. It's not done for us automatically. But now this str label is pointing towards this place in memory, this string. So str is basically equal to this memory address that I showed before, or whatever it is, but it looks like this. So str is like a shortcut for this and can be used anywhere in the code. So yeah, and there is a label that we always must have, and I usually put this on top. It's called start, and by doing global start we specify that this should be exported, so it can be used by other programs, and more specifically by the operating system when we execute the program. So let's define this start like this, and that means that the instructions that we put right here will be executed when we start our program. Okay, so we need to talk a little bit about registers as well. So this stuff that we have done thus far, that is with relation to the ROM memory, the internal memory of the computer. But the processor, the CPU, it has its own form of very fast memories called registers. And each register can take one number, only one number, but quite big numbers. So if we use 32 bits as we are today, and in this series, almost all of the registers will be 32 bits, which is 4 bytes. And if we have an unsigned integer, for example, that means we can go from 0 and all the way to 4.3 billion. So that we use those registers for a lot of different things. When we do calculations, for example, like plus or minus, sorry, or stuff like that. And we also use them when we want to pass arguments to a function and get a return value. And the registers, I'm not going to show all of them, but the ones I use the most. So we have EX, EBX, ECX, and EDX. And these are used when, EX. And these are used when doing calculations, for example, but also when executing system calls. So system calls is a specific type of function which is calling a function in the operating system. So if you've been coding C, you have probably used exit sometime, and that is one of the system calls. Also write and open and read and some others. While stuff like printf or fopen or fclose, etc., those are based in the libraries, in libc to be specific. So we need to differentiate between system calls, which we can call directly from assembly, and library calls, which is possible to use in assembly, but it's a little bit more complicated. Then we have some other registers. We have EIP, which always points to the current instruction. And we have ESP, which is the stack pointer, and EBP, which is usually the saved stack pointer. I haven't talked anything about the stack. The data segment uses global variables. If you have used a static keyword in C, for example, that is similar to this. But the actual local variables of a function in C, those are put on a stack. So the stack is like a stack. You push stuff. If you have been coding any JavaScript, for example, you have used arrays. So if we start with an empty array, we can push something to it, like a string. Hello. And then we can push something else, and then that grows. And we can pop stuff from the stack as well. So if we push two values, we can pop them. So when we push, we put them on the stack to save them for later, and then we pop them. So we bring them back into a register. Okay, enough theory. Let's code something that works. So, doesn't quite look right. I think it should be big S. Okay, so let's start by doing the C function call exit 5. So just quit the program with a 5 as a return value. And all system calls have the same structure. We use the move instruction, which copies something into a register, and we want to move into EX. So the first argument of move is always where we want to put something. And what we want to put in EX. In EX we put a number corresponding to that system call. So every system call in Linux has a specific number. That's how we reference them. So if I save this, and let's see if I can find the file that specifies all of these. Here we are. Okay, so exit is first, then we have fork and read and write, so on and so forth. So that is what we put in the EX register. And I am currently in this directory. User include x86 64 Linux GNU ASM, and the file was unistd32.h. Let's go back into temp and ASM and hello. Okay, so if we want to do exit, let's put a 0 inside of EX. And we have one argument, the return value, and the argument will be put into the EBX register. And we put a 5 in there. I think we said 5. So basically, if we have more arguments, like the read function, for example, have 3 arguments, then we utilize ECX and EDX as well. So that's how it works. Okay, so int 0x80, that initializes a system call. And to sum up, we put into EX the number of the system call, in this case 1 for exit, so not 0, we put 1 there. In EBX we put the return value, the first argument, and then we do the interrupt. So this should exit the program with number 5 as a return value. So let's save this one, and the compilation, so to speak, it's not really compilation, it's more of an assembly, but it consists of 2 different parts. So the first thing is converting the assembly instructions to machine code, and we do it like this. NASM right, we need to do like this. I missed one step. So NASM, we need to specify that we want an ELF64 binary. So it knows what kind of executable file to, in the end, produce. And this time we should only be needed to specify the file name. There we go, hello.o. So let's do an obj dump. That's a disassembler tool, which basically takes a binary executable file and it brings out all the assembler instructions in it. And you can run that on any program binary, really. So, as we can see, we have these 3 instructions, and this is another assembly standard. So as you can see, it looks a little bit different. Move is the same, but we have a $sign in front of the one, and we put the register as the second argument, not the first, and it's prefixed by a % sign. So this is another way of describing the same CPU instructions, and it's still the same type of assembler, but it's just a different way of looking at things. So this is a standard way when using objdump and the GNU debugger. But it might be a little bit messy to think about if you look at it from a new perspective. However, it's the same thing. Okay, so that's step number 1. The second step is to link everything using the linker tool from Binutils called LD. And we just do LD hello.o -o and the name of the final file, hello in this case. So if we have additional libraries, like if we want to include the C library, or if we have several files maybe, then we can specify all of these .o files and create one single binary out of everything. But we only have one, so the command is pretty simple. And here we have the final output. And if we do file on that binary, we see that it's an ELF64-bit. And maybe I should explain that this Linux machine is using a 64-bit processor, and it's the 64-bit version of the operating system. So that's why we create a 64-bit ELF binary in the end. But the language that we use to create it is 32-bit assembly. So that's how it all works. Okay, and one other thing, if we do objdump on this file, then it gets a little bit messy. No, that's only if we link in other binaries. Never mind. Okay, so let's run this one. And we don't see much because the only thing it does is quit the program. But if we add an ampersand and hammer the enter a couple of times, then we see exit 5. So that's one way of checking how the return code looks. Another way is doing an strace. So we see all the system calls and we get exit 5. Third way is running binary like this and just echoing out, I think it's $? Yeah, so this shows the last program's return value. But we're going to use a fourth way, and that is using the GNU Debugger, and we're gonna use this a lot during our. Okay, I need to install that. Let's wait with the GNU Debugger to the next episode. It'll take quite some time for me to download because I only have very slow connection due to my faulty router, but I will prepare it for the next lesson instead. But what have we learned today? We have learned the basics of composing an assembly file with the 2 or more different sections of the memory. The text is used for code, and the data is used for variables and its data. So we use 32-bit assembly. Global start, that means that we are exporting this label. So it's like doing extern and then int main, etc. in C. We are exporting a function. And the start function is always the thing that is the entry point to the binary. That's what gets executed first when you start up the binary. And then we have a couple of instructions. I have described what a register is. That's basically a small memory unit physically on the CPU. And there is like 16 of those or something like that. And you can put one number in each. And you can also access parts of these registers. For example, EX is 32 bits, as we have talked about. But we can also access AX without the E. And then we have half of that register. We also have A high and A low, so we get 8 bits, and so on. That was just a little parenthesis. And in order to execute a syscall, which is a function in the operating system kernel, we put in the syscall number into EX, we put in the first argument into EBX, and we use the interrupt keyword in order to do an interrupt of 80 in hexadecimal form, which initializes a system call inside of the operating system. Okay, that's quite a lot for one lesson. A lot of theory. Hopefully you can use this later on as well, and maybe go back to this episode and replay parts of it. Hope you enjoyed it. Don't forget to subscribe so you know when the next episode airs, and to get more content like this. Thanks for watching, and thanks for today.